Hey guys, today we're going to talk about controllability. So last time I introduced several different concepts that people generally look at for just system analysis. Um, so this time I'm going to hone in on controllability in particular, and then I'll go to observability next class. But recall that, I'll just remind you what you watched last video, that controllability is defined as follows. All right, so we have a dynamic system, and this can be a linear system, a nonlinear system, a time-varying system, a time-invariant system, an autonomous system, a non-autonomous system. Pick your system definition that I've given during classes. This definition's general. So the system with an initial condition let's call it x naught is equal to x of t naught is equal to x naught. This system is said to be controllable to a state. In the last definition I said envelope, but we can consider it as I mentioned that we can consider it as just a point at time tf, which is greater than t naught, if there exists an input u of t such that x at the solution at time f is equal to the state point x sub f. All right, so what does this look like? I drew a picture, a pretty subpar picture last time, but let's look at another one. Let's see, let's do it this way. Maybe I can zoom in. Great. All right, so we have t here on the x-axis, and then we have x of t on the y-axis. We have an initial time, t naught, and then we have a final time, t sub f. We have an x at t naught and an x at t sub f. Okay. So we have this position, and then we have a point out here. Okay, so a system is controllable if you can get an input that takes you from this initial point to this final point by way of a control. So if we could have a control vector that takes you from along that trajectory, we could have one that takes you along this trajectory. It's not necessarily unique. It depends on the system and your methods. But so this guy right here and this guy right here, these are state trajectories or potential state trajectories. And then we could have, let's put our inputs in red. And then, like I said, we are applying an input to at each time instance onto these two signals that drive, again, from this initial point to this final point. So if we can find if there exists even a single control input or signal that takes you from x naught to x sub f, then we have controllability, that our system is controllable. All right, so hopefully that makes a little more sense than the last picture that I drew. All right. So we're going to consider, oops, let's do black again. Let's consider the following system. We're going to consider just a linear time varying. Remember, time varying is when the matrices A and B are functions of time. And then we could have an output and an initial condition. Great. Okay, so now there's a theorem that provides us controllability if we can find that a matrix called the Gramian or controllability Gramian is non-singular, okay? And so namely, this continuous time system is controllable, right? That's the goal. From any initial state x sub t naught is equal to x naught to any arbitrary state x sub f at time x sub f time t sub f, which is larger than x naught, if and only if the matrix here, let's call it W. This is the controllability Gramian. W of t naught tf is equal to the integral from t naught to tf of the state transition matrix times the controller matrix times the transpose of the controller matrix times the transpose of the state transition matrix. Okay, so now if this matrix is non-singular, then we have that our system is controllable. Okay, so we can get from any point to any other point. However, what's nice about this controllability Gramian is that you can actually use it to define your input to actually get you from the state, your initial condition, to the final state at time tf. And so to do that, so to determine a valid control input, take this solution from x naught to x sub f. We can follow the following steps. So step one is first compute the state transition matrix. Okay, so that's phi sub of t naught tf. Okay. Next, to determine the matrix the controllability Gramian by by solving, determine the matrix W. Next, move that over a little bit. Okay, so next we can define this vector. Let's call it D. This vector is going to be equal to the state transition matrix times the final state minus the initial state. Okay, so this is a vector that's essentially pointing you in the direction of the dynamics between the initial state and final state. Next, we can use a Gaussian elimination to determine whether the linear equation W T naught TF times A is equal to D has a solution. So if we can find A, so if it does have a solution, namely if A exists, then the system can be controllable. And why is that? Well, it means that the matrix W is non-singular, right? If A has a solution. And it can be controlled from X naught to XF. Now, if it doesn't have a solution, then otherwise it cannot. Therefore, it's not controllable. All right, so lastly, if we can find such an A, which is the solution to this guy, okay? So if we can find that A, then we can define our input as U of T is equal to D transpose T, because remember this is a linear time varying system, times the state transition matrix TF times that vector A. And so then if we take this and apply it into our system, so now we can take, if we have our system here, this is our linear time varying system, and we have our input U here, then we get the result that we want. Note that this is not using a feedback law. This is just what's called a feed forward control. Great. So now what's cool is that if we have a linear time invariant system, so if the system is time invariant, then we can define the controllability matrix as A, which is equal to B times AB times A squared B dot dot times A to the n minus 1 times B. Okay, so now K is a matrix where each of these elements, B, AB, A squared B, all the way to A, n minus 1 to the n minus 1 power times B. And note, so we can note that the elements in K, namely B, AB, etc., etc., these are what's called block matrices, are block matrices. Okay, and also note that A squared B is equal to A times B. Okay, pretty simple. So what we can do with this controllability matrix, which I'll just rewrite here, that the controllability matrix is K E A B. All right, just wrote that really fast. Then the time invariant system say linear continuous time, just to cover all our bases there, is completely controllable if and only if the rank of K is equal to the size of the system N, is equal to N. All right. And then recall that the rank of a matrix is the number of linearly independent column or row vectors. So this is pretty cool, right? So if we can find, so if our system is x dot is equal to ax plus bu, right? And so we have A, and we have B. All we have to do to determine the controllability of our matrix, of our system, namely that if our system, and again, our system is completely controllable if it can go from any one point to another point. And so we can determine if that's true, if we can find this K matrix, this K matrix here, such that either every row vector or every column vector, row vector or column vector, right, has at least rank n. Well, if the matrix has rank n, which means that there's n linearly independent column vectors or row vectors. K is usually much larger than just n. It tends to be a long matrix. But as long as n of those rows are linearly independent, so if you take the row reduced echelon form of it, you get 1, 1, 1 in some in some element on each row, and you don't have one that's all zeros, then you know that you have n linearly independent vectors. Okay. And so once you have n linearly independent vectors for your matrix K, then you know that your system is controllable. Now you can find a control input. You know that there exists a control input at least that takes you from your initial point at your initial time to your final point at your final time. Okay.